Hello everyone, I'm Karina Chung, and I'm here to present to you today my research on crop yield prediction using Sentinel-2 satellite imagery and an integrated weather and air pollutant data layer. Right now, food insecurity is one of the most pressing global challenges. There are a staggering 821 million undernourished individuals. And as you can see here, acute food insecurity has also risen sharply, especially over the last 2 years. Ensuring food security now and in the future will be challenging. Due to climate change and rising temperatures, crop yields are decreasing and will continue to decrease, as we can see with the projections for corn and rice yields. But we do have a solution to adapt to these issues, and that solution is early warning systems. Early warning systems allow farmers to understand how the climate affects their crops and prepare for food shortages in advance. Nowadays, our early warning systems are getting better through satellite images, like those collected from Sentinel-2. Satellite images capture up-to-date global land use and crop growth. But even so, existing early warning systems are limited. The data they use is often restricted to 1 or 2 countries, so it's difficult to translate their approaches to other global use cases. Many also don't cover multiple crops at once, leaving out some of the world's most important staple crops. Lastly, they often overlook important air pollutants like ozone, nitrogen dioxide, and sulfur dioxide, which have all been shown to decrease crop yields. Simply put, few approaches have used satellite imagery and the necessary atmospheric data for accurate crop yield predictions. So this summer, I set out to create an open-sourced, comprehensive, and translatable early warning system. This flowchart shows all 4 phases of my proposed system, from classification to implementation. During my 6 weeks at SSI, I worked on phases 1 and 2, crop type classification from Sentinel-2 satellite imagery and the supplementary data layer. One of the biggest goals of my project was to develop a transparent procedure to generate a clean satellite imaging dataset ready for use in machine learning. Existing procedures are often not detailed enough to be reproduced adequately. I also created the supplementary data layer, a novel dataset which contains weather and air quality data covering the pollutants that are often untracked, like I mentioned earlier. The chart here shows my data generation procedure. I isolated 5 areas of cropland, 3 in Arkansas, 1 in Tennessee, and 1 in Kansas. From each region, I captured 4 images, 1 for each season. Through this procedure, I converted the images into numerical arrays for use in machine learning. In the future, I plan to open source this code so anyone can use this procedure for their own research. My initial random forest classifier achieved F1 scores comparable to other ensemble models tested in the literature. To dive into the model performance further, here's a confusion matrix showing the prediction accuracy for each crop. As you can see, the diagonal is very clear, indicating mostly accurate performance. I also want to highlight the metrics for 4 global staple crops: corn, rice, soybeans, and wheat. I also want to draw your attention to this column, which shows some erroneous predictions for soybeans. This result makes sense, as we've used a relatively small dataset, and soybeans is the most common class. For additional model evaluation, I performed a bi-location cross-validation. By that I mean, out of the 5 locations I collected, I trained the model on 4 and tested on the remaining 1. Here we can see a clear disparity in the F1 scores. For location 1, we see a lot of error, but for locations 2 through 5, we see excellent performance. In fact, it's far above the overall F1 score around 0.7 from earlier. Let's take a closer look at location 1. In this confusion matrix, we can again see this column for soybeans, but it's much more pronounced, and the diagonal is not clearly visible. This pattern further shows the class imbalance in our small dataset, and suggests that the results can be improved through collecting additional data for the model to better capture the variety of crops in location 1. We plan to collect this additional data from the Pacific Northwest, where there's more corn and wheat, and less soybeans, to hopefully balance out the dataset. In contrast, testing the model on locations 2 through 5 generates very accurate predictions, as you can see with the clear diagonals in each of these matrices. So what did my research accomplish? Well, I created an open-sourced translatable early warning system. I also created a transparent procedure to generate two novel datasets, the images I collected from Sentinel-2 and the supplementary data layer. I've obtained initial classification results comparable to other tested methods and shown excellent accuracy in 4 of the 5 tested locations. My results also show some very clear steps for improvement. So in the future, I plan to refine the classification model and test other machine learning techniques like neural networks. I also plan to develop phases 3 and 4 of the proposed system, yield prediction and practical implementation. These are very important next steps towards building an early warning system to address widespread food insecurity. Nevertheless, these solutions can't wait, and we need as many people working on them as possible. So to conclude my presentation today, I'm issuing a call to action. As a community of motivated researchers and data scientists at SSI and beyond, there's a lot that we can do. For example, just a month ago, South African officials released a hackathon, the Spot the Crop Challenge. They call for any and all data scientists to create crop classification models from Sentinel-2 satellite imagery, just like I've done in this project. I encourage anyone who's interested to pitch in, not only during this contest, but also in the future to help build a hunger-free world. Lastly, I'd like to thank my mentor Carter for all his excellent guidance this summer, as well as my lab group for their feedback. I'd also like to thank the SSI staff and my family for supporting me throughout this process. Hope you all enjoyed the presentation, and thank you so much for listening.